Good morning, everyone. We're going to pick back up here in chapter 9 this morning. Just a few things. So yesterday, of course, we didn't have recitation, so we're asking that you just find the activity, attempt the problems, show your work, submit those by Friday to your TA by email to get the points for the week. There's a video, so you can just watch the video if you need help doing any of the problems to kind of replace having a recitation. I think it's still important to look at those problems and to have a chance to see them to help prepare through chapter 9 and through section 9.6 for next week's midterm, next Tuesday. Another reminder is next Monday is a holiday, so we don't have lecture next Monday morning. And so therefore we don't have the Monday review before class, of course. I will have, and I sent a link out for this already, I can resend it towards the end of the week, but I'll have a review session on Zoom, like a Q&A session, and I'll go over some review problems if there's no questions or after questions are over for about an hour and a half on Monday afternoon starting at 1:30. And then Dr. N's review is tomorrow night. So as usual, she's doing a review, and it's going to be broadcast on Zoom as usual. I sent an announcement, I think last Friday, with that information. So you can find that on Carmen or in your inbox. Okay, so coming back into chapter 9 here. So section 9.4 deals with the sort of idea that bonds can be described in some ways by orbital overlap. So if you picture or think about the H2 bond, you can maybe picture or think that each of the H atoms has a 1s orbital. And if you can imagine the overlapping of those two orbitals is kind of the explanation of how the H2 bond forms. And so the idea is that orbital overlap is one way to explain bonding. And so you can then start to understand other types of molecules like Cl2 or F2, cases where you have a halogen that if you're thinking you have like a chlorine molecule that's deficient of an electron here with a lone pair or just a lone electron that can overlap with another chlorine's electron, it kind of gives you an idea of thinking, well, what orbital would that likely be for chlorine? And for chlorine, its largest orbital, like if you're thinking of the electron configuration of chlorine, you'd probably be thinking it's a 3s2, 3p5 in terms of its outer valence shell. So spin pairing in the 3s, and then in the 3p, we'd have one unpaired electron in a 3p subshell. Let me show this a little bit more clearly again. So we'd have 3 electrons up, 2 electrons down. So we'd have this one electron unpaired, and that unpaired electron would be in a p orbital. And so if you're picturing a 3p electron for one of the chlorine atoms, just imagine it overlapping with the 3p of the other atom. And so you get this idea of orbital overlap. The overlapping of those orbitals is an explanation for what that bond looks like in something like Cl2. And so this is going to send us for a lot of other molecules in terms of, things like methane or formaldehyde, BF3, molecules of that nature. It's going to send us into kind of a situation where the orbitals of the atoms don't really line up where we need them to be to get orbital overlap. So we're going to see that we do something called mixing or hybridization for things like sp2, sp3 orbitals. So we'll talk about those in a minute. But for now, what I want us to think about is kind of what these diagrams look like here, where we can describe a bond being formed like H2 as the two hydrogens being separated. If we bring the atoms closer together, they experience an attraction together due to forming this bond. So instead of it being, if you recall, plus minus ions do this, where we get this attractive force, well, two neutral hydrogen atoms have this attractive force where they're forming that covalent bond between the two atoms. Once you get down here, this is where you have the H2 molecule formed with its ideal bond distance of about 0.74 angstrom. So that turns out for H2 to be its ideal bond distance. And if we keep pressing the atoms closer together, then the energy would go up. So the energy increases here if you try to push the atoms closer past their ideal bond distance together. And so the idea then is once you have this bond here, in order to break it into two H atoms, that requires energy. So the energy takes to go from the bottom of the well to separated atoms, that this difference of energy here is equal to our bond strength of H2. So that's equal to the bond energy of H2. If you recall, that's a positive quantity for all bonds. All bonds take energy to break. For H2 out of chapter 5 and chapter 8, where we talked about bond strengths, this is about 436 kJs per mole. So we kind of have a good idea of what that energy is from some numbers that we've seen from a chart. We could look it up. I don't expect that you have that number memorized. But for H2, it takes about 436 kJs per mole. And we can then think for like single versus double versus triple bonds that there's a dependence on bond energy and bond length as you kind of compare these different bonds here. So our single bond is going to be longer and weaker, the double bond shorter, stronger, the triple even shorter, the strongest of the three. So if we're thinking in terms of length, the carbon-carbon single is longer, the carbon-carbon double is shorter, and then the carbon triple bond is the shortest in terms of our bond length. And then in terms of bond strength, of course, it flips that the carbon-carbon triple bond is the strongest, then the double, then the single. And so how would their diagrams look? So if we're thinking of the potential energy surface diagram for carbon forming single versus double versus triple bonds, just to give you a little clue here of what molecules look like that do this. Of course, ethane has the single bond, so CH3, If we had CH2, that would be a double bond to carbon to CH2. And then if we had CH, that's going to be a triple bond to CH. And so just to show one of these real quick, the CH, this looks like carbon-carbon triple, each one with a hydrogen, linear bonds on both sides. The ethane would look like two tetrahedral carbons because we're going to have 4 domains on each carbon. We'll see structures of that, something like that in a minute. The CH2, we'll see that in a little bit too, but that's going to look like two trigonal planar. So we're going to have 2 hydrogens on a carbon, and then with a double-double bond in the middle. Okay, so if we're thinking of the potential energy surface for the carbon-carbon bond, so just think sort of at 0 we're here. And so we're going to have our carbon-carbon atoms separated. And so then if we're thinking of, like, let's start with the carbon-carbon single and just kind of draw like a general diagram in here. So just think this is our single bond. What do you expect the carbon-carbon double bond to look like relative to that bond? So the carbon-carbon double bond should be shorter. So the bond distance for carbon-carbon double should be shorter. So it should be to the left so that the bond distance is shorter, and then deeper because it's stronger. So the carbon-carbon double, change colors here, should look for the double bond something like this. So it's to the left, so the bond distance is shorter. And then the potential well is deeper because the bond's stronger. And then if we go to the triple bond, should be even shorter, even stronger. So not a big detail, but there's been some practice exam questions that kind of compare 2 bonds on a diagram like this. And you're just kind of comparing bond distance left to right. So a longer bond should be to the right to a longer distance. A shorter bond should be to the left to a shorter distance. And then you should be deeper into the potential well for a stronger bond, one that's harder to break. And you should be higher in terms of this energy, in terms of a bond that's net weaker. Okay, so that's how we can compare what kind of different bonds look like in terms of their diagrams. It's like if you could strengthen the H2 bond somehow, you would make the potential well deeper. And if you could shorten the bond, it would be to the left in this diagram here. So just something that strengthens the bond makes it look in this direction over here. Okay, so now when we look at other molecules, we can start to kind of think, okay, like how can we describe the orbitals that are giving us the overlap? Let's start with things like BeF2, and also we'll see CO2 kind of fits into this model here. So we're kind of looking first at molecules that are linear. So let's try to describe the type of bonding that goes on in molecules that fit into a linear molecular geometry. Obviously, BeF2 would be linear as well. If you recall, from a Lewis structure standpoint, beryllium would have 2 electrons. Fluorine would have its 1 electron here. Now, the issue is that for BeF2, what you might think is that you have this like 1p orbital that has that lone pair electron. Well, that gives you a good model for one of the bonds, but then you don't get good overlap with the other fluorine because there's like already filled electrons in that p orbital. So the problem with the orbital overlap that we did for like Cl2 is when we're looking at Cl2, when we make this bond here by overlapping the p orbital, so if you recall we started here, that we make this bond over here, that uses up that p orbital, and there's nothing available here to bond with. So like Cl2 forms, we don't get another atom attaching to Cl2 because there's already enough electrons in that p orbital of Cl2 once it pairs up with the other chlorine atom that it can't make a second bond on its other side. And so for that same reason, BeF2, we can't really describe its bonding by just looking at one of its orbitals. So what we have to do for beryllium is realize that, well, beryllium's in the second row. Well, what if it uses one of its 2s orbitals and one of its 2p orbitals? And so instead of thinking of beryllium, in fact, if we're picturing the p orbital of beryllium overlapping with fluorine, beryllium kind of has a base configuration of 2s2 as its outer valence shell. So beryllium kind of really just looks like an s orbital. So if we're really thinking of what beryllium looks like, it really kind of just looks like an s orbital. So how do we get overlap with that one s orbital with it's already filled with electrons, so it doesn't really need to share those electrons with other atoms to become quote unquote more stable. So what does it do? Well, one of the bonding models says, well, what if we take the fact that it's in the second row and has access to the 2p subshell, what if we take these two orbitals here and hybridize and mix them together? The hybridization process, I should mention, is completely fictitious in a way, but it's done in a way to try to give us a model to try to understand why we get the bonds that we get in molecules that form. So what we do for beryllium is we take an s orbital and one of its p orbitals and we quote unquote mix them together. So we take what looks like an s and a p and we end up getting orbital number 1 and orbital number 2 pointing in that 180-degree direction that we know we want the orbitals to point because we're trying to describe linear molecules. So what we've done is we just kind of created having one electron in each of those orbitals. So we kind of created like fake p orbitals, if you will. It looks like kind of like an unbalanced p orbital, but one on one side, one on the other, each with one electron so that they can pair up with things like fluorine. So we can take a fluorine atom, which has its largest orbital that's unpaired as a 2p orbital. So then we can pair and overlap and get this overlap that we want to get according to covalent bonding theory, or according to this theory that says we should get orbital overlap to make bonds. If we have a bond, there should be orbitals overlapping to give us those bonds. So because we can't natively get the overlap with the orbitals we know beryllium has, we create this hybridization process, or this hybridization picture, to get the overlap that we think we want to get to understand the bonding in this molecule. So we look at beryllium and say that beryllium just takes these two orbitals here, and instead of those two orbitals looking like that, they hybridize and change their shape such that beryllium has one orbital pointing here and one orbital pointing here, each with one electron ready to overlap and pair up with something else with one electron. And so then that helps us describe the bonds in beryllium F2 down here as being sp hybridized for beryllium and then overlapping with the 2p orbitals of fluorine. So if I'm describing this bond here, I describe this bond here as the sp overlap of beryllium overlapping with the 2p orbital of fluorine. So we call that like sp 2p overlap. Okay, so we're hybridizing an atom in order to get this hybridization set. Let me actually, this probably is on another slide later where I come back to multiple bonds to describe multiple bonds. So I'm kind of getting ahead of myself with CO2 a little bit, but at the same time, I want us to kind of picture what CO2 does in a similar way, but then how it has extra orbitals that are unhybridized that are left over in order for us to make these multiple bonds that we have on either side of CO2. So if we're thinking of carbon here, carbon has kind of the same picture. If we're thinking just an ordinary carbon atom is a 2s2, 2p2 configuration, in terms of these three orbitals kind of looks something like this in terms of its configuration. So we have our 2s and our 2p. So what if we take and do something like this, take these orbitals here, hybridize those, and make that sp hybrid so that we make sp hybrids but only put 2 electrons into those orbitals. And then we have the unhybridized 2p orbitals. So these are our 2p orbitals that are left over, and these are sp hybrid orbitals that we've hybridized. So it's like the hybridization process is taking orbitals, like our atomic orbitals, mixing some of them, but we still have to get the same count. Like if I'm starting with 4 orbitals on carbon, I end with 4 orbitals, I've just now hybridized 2 of them and left the other 2 as they were. Now, if you think back to beryllium for a minute, if you recall, we started with a 2s with 2, and then the p shell was empty, and when we hybridized, we ended up with 2 electrons in the sp, and then the other 2p orbitals were empty. They didn't have any electrons. And if you look at beryllium, it doesn't do anything. Like those orbitals are just empty. So beryllium has 2 p orbitals that it just doesn't use. So to really kind of quickly think of that for a minute for beryllium, it's like we're hybridizing these 2 orbitals here. Well, there's these orbitals still available on beryllium, but that it just doesn't need to use for anything. So it has these like 2 other p orbitals that it just doesn't do anything with. Now, you might understand that beryllium is not very stable, and if you have something with a charge, it's going to kind of go after those orbitals and find a way to use them. So like BeF2 isn't like the most stable molecule. It's not like CO2 that we're gonna breathe it in or anything. Certainly don't want to do that. So it's still a reactive molecule, not particularly stable, but CO2 ends up being stable because it's going to find something to do with those orbitals that we didn't hybridize. And it's good that it'll find something to do with them because we have electrons in them that are unpaired that probably want to pair up with something. And so for CO2, the picture would go like this. Like picture how we have orbitals that look kind of like this that we started off with just like we did on beryllium. And then how for CO2 that they're going to hybridize in this direction here. So we get 2 hybrid orbitals. These are my sp orbitals. And so we get those sp orbitals that are able to then overlap with an oxygen atom. Let's draw a couple lone pairs on oxygen here to kind of give us an idea of what oxygen might look like. In terms of oxygen, we could think that it has 1, 2, 3 domains as well. I kind of almost need to get into the next hybrid set first to really understand oxygen. But let's imagine for a minute that oxygen has a lone pair in one orbital, carbon has its lone pair, or I keep saying lone pair, a lone electron. So each of the sp orbitals on carbon has 1 electron each, and then the O atom kind of brings 1 electron each, and we make an orbital. So we make an overlap between these orbitals here and these orbitals here, where each one of those bonds is like one of the double bonds of CO2. So like half of the bonds in CO2 are described by these hybrid orbital overlapping bonds. But then what we then do is oxygen and carbon has these leftover orbitals. So we have these 2 leftover orbitals that we can then use to make the second bond. We can have those make that double bond of the oxygen. So we have oxygen pair up its p orbital that it also will have left over. We'll see why in a minute when we get to the next hybridization set that we call sp2. But for oxygen, it has a leftover p orbital that it's going to use to overlap to make a pi bond. And then same thing with this oxygen here. So we're going to make those double bonds by something we call pi bonds. And then we're going to have those as kind of part of the process. So when I'm looking at CO2, we're going to have a few pictures later that we come back to hopefully solidify this. But bonds is like looking at this here and seeing that we get a sigma bond and a pi bond. And the sigma bond is this one. It's the one that's on that bond axis between the 2 atoms. And then the other one has the same sigma plus pi. So we get the sigma orbitals on the bond axis. And then the pi orbitals, these orbitals here that we get, those are the pi bonds. And so our double bonds are being characterized by being having a sigma overlap of the hybrid orbitals, and then the unhybridized p orbitals are left over, give us what we call pi bonds. And the pi bond, think of this is the letter P in Greek. So this is kind of P for planar. So it's like a planar bond, and then this is S for like a symmetrical bond. And the symmetrical is like the bond axis symmetrical bond. So one of the bonds is on the bond axis, that's our sigma bond. And one of the bonds is on the plane of the bond, that's our pi or our planar bond. We'll see better pictures when I'm sketching here, but hopefully like if you're kind of getting the idea that CO2 is finding something to do with those orbitals that BeF2 didn't need to do anything with. So the orbitals that we don't hybridize on CO2, on carbon, are left over to make these pi bonds with neighboring atoms like oxygen and CO2. Okay, so like I said, stay tuned we'll come back to CO2 in terms of a picture hopefully on our screen that looks better than the ones I'm sketching here on my screen. So if we then look at a molecule like BF3, so BF3 we know is trigonal planar. So from what we know about the structure of molecules that have 3 total domains is that this molecule should exist in one plane and that those bond angles should all be 120 degrees. So we know this should be a trigonal planar molecule. And so then the question is, well, how do we describe the bonds? So how do I understand how it's possible that I'm getting these bonds here that are forming between boron and fluorine? And it comes down to this problem where if you're looking at boron has access to p orbitals that look something kind of like this. And then I'll show the one in blue kind of sticking straight out of the page. So these are what our quote unquote native p orbitals look like. So how do I get overlap with fluorine atoms that are going to be here? I might be able to get overlap with one of the fluorine atoms, but not the other 2. So I don't see natural quote unquote overlap with orbitals of boron in terms of its atomic orbital. So I have to hybridize boron's orbitals as well. And so the hybridization process for boron will go like this. I need there to be 3 orbitals now because I have 3 bonding pairs. So CO2 and BeF2 only had 2 bonding pairs. So I only needed to take 2 of the atomic orbitals of beryllium to hybridize that into sp hybridization. What I need to do for boron is I need to find a way to take 3 of its orbitals so I can get 3 hybrid orbitals. Because what I really need for boron is I need for it to have 1, 2, 3 orbitals that it can make. And I would ideally like to have 1 electron in each of those to kind of click into a model where fluorine's going to bring an electron. We're going to pair those up, and then we're going to get orbital overlap with those hybrid orbitals. And so then for boron, it kind of goes like this. If you think of the electron configuration of boron, think of the periodic table, it's a 2s2, 2p1 configuration in terms of its electron configuration, of its valence electrons. So we'd have 2 electrons in 2s, and then in our 2p set, we'd have 1 electron. And so like I'm saying, if you just picture the 2s and the 1, 2p orbital, you're not getting overlap with all 3 of those fluorine atoms in BF3. So let's do a hybridization with boron here as well. And so, but let's hybridize these 3 orbitals, and then let's leave behind 1 of its p orbitals. Okay, so what I'm going to do for boron is I'm going to take its 2s and the 2p, let's call these x and y, and let's call this axis here the xy axis. It doesn't matter which one you're calling the x versus the y, but just imagine, the only reason I'm trying to do this is I want us to think, well, which orbital did we not hybridize? So that we can then picture what that is. That's here, that's our pz. So if we're just taking the x, the y orbital, we're leaving behind the z. And so when we hybridize these 3 orbitals, they hybridize here, and then think of how what we're doing is we're hybridizing those into this hybridization set here that we call sp2. S backward, so sp2, and then plus our p orbital that's left over, and it's a pz if it matters. And we'll try to show why that matters later so we can picture the orbital that's left over on boron that's not hybridized. So we come up with our 3 orbitals that are hybridized, each of them with kind of 1 electron, ready to overlap with the fluorine's 1 electron. So we make these orbitals here. And so these are our 3 sp2 hybrids, and we point them intentionally, of course, as we need them to be at 120 degree bond angles relative to each other. And this is where we kind of come back that this isn't, there's no math model that says if you take this in a sphere that it mathematically averages to 120 degree bond angles. I hope you understand this is pure fiction. Like this is purely a model of us saying, well, what if we take these 3 orbitals and just change where they point and make them look where we want them to point so that we get orbital overlap where we think we need to have orbital overlap. It just comes back to the idea, if you have bonds in a molecule and you think bonds form due to the overlapping of atomic orbitals and you don't have an atomic orbital there, you just change the structure of how the orbitals look so you get that overlap, so you get that bonding model picture you think you need to get. And so then we put a fluorine atom over here, and then it has its 2p orbital, so we get the 2p sp2 overlap. Put a fluorine over here, same thing. So fluorine's 1 extra electron pairs up with these orbitals over here, so we get our overlap between fluorine and boron as what we would call sp2 of boron and the 2p of fluorine. So all these bonds here are sp2, 2p overlap. Now for boron, which of its p orbitals was not included and is just empty and not doing anything? Well, it's the one that's perpendicular to all this. So the p orbital that's left over is the one here. So like, maybe that's a bad color. It's probably no good color to choose here. Just use this color here. So sticking straight out of boron is an orbital, an empty 2p orbital it doesn't do anything with. Now, other molecules, like if we start thinking of things that are trigonal planar, but that have double bonds, a molecule that comes to mind is formaldehyde. So formaldehyde looks pretty similar here, and we'll see in a minute, we'll see a better picture later, but this is a molecule we would say is sp2 just basically because it's trigonal planar. We look at this molecule and say it's trigonal planar because it has 3 total domains. These bond angles should be approximately 120. We do know that this bond angle is slightly greater than 120. This is slightly less than 120. So our hybrid model can be flexible. We can make the we can make the orbitals flexible to wherever they need to flex to for our molecule. And so we make our sp2 hybrid orbitals for carbon, and we have them point in these 3 directions here. And then we're gonna find a way to use that unhybridized p orbital to make that overlap to make the double bond. So again, we'll see in terms of slides showing us better pictures of what multiple bonds look like, but double bonds, we'll even see this for triple bonds, are giving us the unhybridized p orbitals overlapping to make those pi bonds. So if you kind of have in your mind here, BF3 has a p orbital that it does nothing with, and somehow still ends up being a stable molecule as a result. The reason why BF3 is probably a stable enough molecule without using one of its orbitals is just because it has the right charge balance. If you recall, BF3, neutral boron in terms of the formal charge, the neutral fluorine in terms of the charge. If we did something to boron that made it use that unhybridized orbital, it's going to put more charge around boron and probably make it less stable as a result. So anyways, BF3, trigonal planar, sp2 hybridized to give us this overlap with fluorine. And we'll see formaldehyde, also sp2 hybridized because it's trigonal planar as well, but then it finds something to do with that unhybridized p orbital. So let's come back to the unhybridized, to what pi bonding really looks like in a few moments. So let's now look at the last hybridization set that we'll look at. This is the case for tetrahedral molecules, so something like CCl4. We know is a tetrahedral molecule because we have 4 domains. We know these bond angles should be about 109.5 degrees. So again, the question would be, for carbon, do any of its orbitals happen to naturally be at 109.5 degree bond angles relative to each other? And the answer, of course, is no, because it has, just like all other atoms we're talking about so far, p orbitals that are 90 degrees relative to each other, not 109.5 degrees relative to each other. So then how do we explain the bonds between carbon and chlorine? Well, we're going to hybridize carbon here. So we look at carbon. We say carbon is a 2s2, 2p2 configuration, just in terms of an ordinary carbon atom. So again, that looks like something like this. So what if we take all 4 of these orbitals here, mix them together, change their shape, and make 4 orbitals that are equivalent to each other, and put 1 of those electrons into each of those, and we call that sp3 hybridization. So the superscript of the p is telling you how many of the p orbitals you've hybridized. So sp hybridization hybridizes 1 of the p's, leaves the other 2 behind. sp2 hybridization hybridizes 2 of the p orbitals with the s, giving us 3 orbitals for like BF3, leaving behind that last p orbital that's unhybridized. And then sp3 hybridizes all the p orbitals, so we have no p orbitals left over for the molecule to use for anything else. So all the p orbitals for carbon are being used in this hybridization set for sp3. So we have an s in these 3 p orbitals that then mix together and give us our 4 hybrid orbitals. And again, picture how we're going to get a pair of, like 1 electron, I keep saying pair, 1 electron into 1 lone electron in each of those orbitals that can then pair up with something like a chlorine atom, which has 1 lone electron as well. So we can then start to picture that CCl4 should have 4 orbitals that look like they're in the direction of a tetrahedron. So we then, when we hybridize the orbitals, we put them where we need them to be based on the geometry we know the molecule has, tetrahedral. And so we get these orbitals, point them in the direction of a tetrahedron, and we get the overlap that we expect. So we get sp3 for describing these bonds here for CCl4. We'd say we get sp3 overlap for the carbon atom, and we're going to get that overlap with chlorine. Now chlorine's a 3p just because it's in the 3rd row of the periodic table. This is our chlorine overlap. We've done a lot with fluorine. If we had CF4 instead of CCl4, then we'd call that sp3 2p overlap. And so the 2 to 3 is just changing for fluorine and chlorine based on what row they're in. And the sp3 here just has to do with hybridizing all 3 of the p orbitals, just to kind of make sure we're seeing the difference between the superscript 3 and the sp3s for hybridizing 3 p orbitals. And then this 3 here is just the designation for chlorine being 3s2, 3p5. So it's just coming from that 3p here. Okay, so for tetrahedral molecules, now they lack that p orbital that's unhybridized. And so when we start thinking tetrahedral molecules, it's going to be hard to come up with a model that shows us double bonds. To take a quick aside, if you recall the SO4 problem, remember sulfate ion, we had this issue of which of these Lewis structures is best. This one. So we were like, is this Lewis structure better, where we have a minus formal charge oxygen atoms and then a 2+ sulfur? Is that better? Or is it better to have this Lewis structure here where we have 0 formal charges here and then a minus here? And the explanation we gave was that we were not going to ask you in the test which one of these is better, even though this one's better. Like categorically, that one's better. But we're not going to ask you which one's better on the test, just because the book doesn't make it crystal clear. Some other teachers disagree with me on this, and they're welcome to disagree with me and present their arguments. But like some people think this structure is better, and I really don't understand why they think that's better. But when I come back, and the reason why I think it's kind of good for us to think that this model here isn't good is how am I going to get these double bonds here? Double bonds we're going to see that they form from unhybridized p orbitals that are overlapping with each other. Well, SO4, no matter which of the models you're looking at, should be tetrahedral. If you have a tetrahedral sulfur, there's nowhere to make these double bonds. So I just can't come up with a picture where we're going to get double bonds and then how they can possibly then spread across the molecule through resonance. We're going to see some nice resonance pictures. We've already showed you the nitrate ones, but we're going to see some nice resonance pictures that emerge when molecules are generally flat and they have an overlapping network of p orbitals that simultaneously overlap together to give us what we think of as being resonance. I don't get that with SO4, so I think that's a good reason why this structure here with the double bonds is not a good one. So double bonds, I need there to be unhybridized leftover p orbitals to make those double bonds, and I just don't have those within an sp3 hybridized central atom. Okay, so that just is a quick aside on sulfate. We'll come back to things like nitrate and then other molecules that have resonance in a few moments. So let's look at C2H4. So C2H4 has that carbon-carbon double bond, 2 hydrogens. The structure's here. I don't know why I'm sketching what's literally right here. But in terms of our Lewis structure, this is kind of what it looks like, where we have 3 domains, so 1, 2, 3 total domains. And those bond angles should be approximately 120-degree bond angles relative to each other. And a slightly tricky question is, well, are these perfectly 120? Probably not. The 2 single bonds probably get a little bit closer together, and the double bonds probably get a little bit further away. That 4 electrons in carbon-carbon probably press the 2 single bonds to be a little bit closer together, but the molecule is still perfectly planar. And so by planar, I mean all these bonds here are in a single plane. So all those bond overlaps are in a single plane. Hopefully we can understand why the molecule doesn't have 2 of the hydrogens in a different plane relative to the other 2 hydrogens. Why are the 2 hydrogens required to be in the same plane as each other? Well, let's take a look at the way the orbitals overlap. And so let's also take note that this picture, maybe this is helpful for me to have sketched this here so that we can picture this molecule here. And I just want to rotate it in my paper so that my hydrogens are sticking out and going into the plane. So if you can picture this here where this hydrogen's coming out at us a little bit. So imagine this hydrogen's wedging outward and then this hydrogen's going back. Can you picture that in your paper where the molecule really is kind of looking like it's sticking straight out of your paper? That'll help us understand some of the orbital overlaps in the pictures we get. So if we're picturing, and hopefully you can see that these diagrams here, I think you can still picture that way, that those atoms or orbitals are pointing straight out and into the page. The hybridization set I should use here is sp2 for carbon because those are trigonal planar carbons. So sp2 hybridization. So that means I should have, 1, 2, 3 hybrid orbitals for each of those carbon atoms. And so carbon goes sp, that's the purple orbitals. And so then the purple orbitals, each of these have a lone electron. And the lone electron on the outside can pair up with a hydrogen atom. That's shown here. Again, I don't know why I'm sketching, but I'm just trying to picture it. Hydrogen has a lone electron. There's a lone electron in the external, the outer hybrid orbitals that give us those bonds to make the hydrogen overlaps. And then the internal electrons overlap with each other. So the two hybrid orbitals in the middle, the sp2, sp2 orbitals overlap. They make what we call the sigma bond. And so that's our sigma bond here. And so this bond here, I call that the sigma type, as opposed to the planar type. So think, is that symmetrical about a bond axis, that sigma, or is it symmetrical about the bond axis plane? It's symmetrical just about the axis, so that's our sigma bond. So the sp2, sp2 orbitals overlap to make a sigma bond. And then what about these two guys here? What about these two orbitals here? Those are our leftover p orbitals. Now, the question I think would be, how do you know that they have an electron in them that are then gonna overlap together to make a pi bond? Well, just think about carbon for a minute. So each of these carbon atoms should have been 2s2, 2p2. And so when we hybridize into sp3, 3 of the 4 electrons go into the sp2 hybridization, and then we leave behind that p orbital. Let's call it the pz. It doesn't matter which of the p's it is. It's just the p orbital that's unhybridized is the one perpendicular to the plane of the other 2 p orbitals we hybridized. That's the key detail. The key detail is that this orbital here that's left over is perpendicular to the other 2 orbitals that we've hybridized. And so that's why I think it's important to picture the 2 hydrogens sticking straight out of the page, because those 2 p orbitals are gone, they're hybridized in the sp2 set. The one left over is the perpendicular one. The perpendicular one can only align with the other if it's also perpendicular. So like the 2 p orbitals, they have to align to overlap. And if I have the 2 hydrogens, one's here and the others, if the 2 hydrogens are bisecting each other, think about how the p orbitals, now one's here and one's here, they don't overlap. I need the hydrogens to be in the same plane as each other in order for these 2 p orbitals here to be able to overlap together to make that pi bond. So this is our pi bond, and it's arising because there's an electron in each of those bonds, each of those orbitals that can overlap together. So in order to have an orbital that's used, we have to have electrons in that orbital. So we put 2 electrons into this pi orbital. And so we have, for carbon-carbon double bond, we can look here and say that that's the sigma bond, and then it also has the pi bond. So like a double bond is comprised of the sigma overlap of the sp2, sp2 orbitals, and then the pi orbital from the overlapping p orbital that we get. And then this bond here, I think you can agree that's planar. So that's why it takes the designation pi. It's like a planar type orbital. It's not symmetrical about the bond axis. It's not symmetrical about this axis here. It's symmetrical about the plane of the bond. So it's a different type of bond than our sigma bond. And so generally speaking, if we see a double bond, it's going to be a sigma and a pi. And then what about a triple bond? Let's take a look at acetylene, CH2CH2, or C2H2. And so this is the structure here, where we have these internal 180-degree bonds. If I'm thinking my hybridization set here, I only need sp hybridization for those 2 carbons because they're linear, not trigonal planar, not tetrahedral, so they're just sp hybridization. And so that leaves behind 2 p orbitals. Let's call this axis here the z-axis. So if we're hybridizing the pz, I don't know why I'm choosing the z-axis, but I think it's common for whatever reason, we set the z-axis in a linear molecule to be the bond axis, then I have my px and my py left over. And so if this axis here, again, this is my z-axis, then this is my p, let's call this the px, and call this the py. And C2H2, again, we had carbon that was a 2s2, 2p2 to begin with, was initially this, and then we hybridized it to be sp, with 2 electrons each, and then our px and our py, each with an electron as well. And so for C2H2, we should be able to take each of the two carbons, they're sp hybridized each, and so we have our sp hybrid orbitals, each with an electron, so we get an internal sigma bond. So the sp-sp overlap gives us our sigma bond. We call that sp-sp overlap, giving us the sigma. And then we have the other sp orbital, a lone electron that can pair up with hydrogen's lone electron to make the CH bond. So we have the 1s sp overlap to make the CH bonds on either side of our molecule. And then we have each of these p orbitals has an electron that can overlap. We make one pi bond, and then we can make our second pi bond with the other electrons that are unhybridized. So we have electrons in the unhybridized p orbitals that can overlap with the other electrons in the unhybridized p orbitals to line up and make these multiple bonds. So for carbon-carbon triple bond, we look at this molecule here. We know that the triple bond arises from the one sigma that we get. So we get just one bond in the middle, then we get the two planar type bonds. So we get bonds for the triple bond. And then what about the singles? Let's make sure we're classifying the single bonds correctly. These bonds here are symmetrical about the bond axis as well, so those are sigmas. So sometimes we'll show you a structure like a Lewis structure and say, well, how many total sigma and pi bonds are there for the entire molecule? So the total for the molecule would be 3 sigma plus 2 pi bonds. So the triple having the 2 pi, but a sigma, and then each of the CH single bonds are sigma bonds. And so what this comes down to is a single bond is a sigma, a double bond is a sigma plus a pi, and then a triple bond is equal to a sigma plus 2 pi bonds. And the extra pi bonds, those are bringing the nuclei together. So like having those extra bonds, shortening the bond in the process, strengthening it as well. So again, this is just another picture. There are multiple bonds. We get our sigma bonds. The sigma bonds are on the bond axis, so they're the bond axis symmetric. So I'd like to think sigma for S for symmetrical about the bond axis. And then our pi bonds are planar type bonds that are symmetrical about the bond plane. So those are our pi bonds. And so we get 1 sigma for H2. For the double bond in ethylene, that's a sigma plus a pi. The triple bond in N2, we can describe that as being a sigma plus 2 pi bonds as well. Because here we could look at either of those nitrogens and think about those nitrogens being sp hybridized. And so let's think about nitrogen real quick. So nitrogen is a 2s2, 2p3 configuration. So in terms of its atomic orbital configuration, looks something like this. And so if we're going to hybridize the sp orbitals here to be this, and then we're going to leave behind the px and the py, what ends up happening is, if you think of the balance of electrons, is we're going to have 2 electrons, we're going to have 2 electrons in one of the sp orbitals, and then we're going to have 1 electron in the px and the py. And so we're thinking about nitrogen in terms of its bonding and how it can look in terms of a hybrid orbital picture. We can have nitrogen with an sp orbital on either side, but the lone electron pairs up, and then we have 2 electrons over here giving us that lone pair. So a lone pair, electrons here are just in the sp orbital, but they're spin paired. So once you have 2 electrons in a hybrid orbital, it doesn't have room or the ability to share those electrons with another atom. So think about why does N2 not form like a hydrogen bond? Why does H atom not pair up with nitrogen on either side to make H2N2 like we have H2C2 or C2H2 for acetylene? Well, the answer is we already have 2 electrons. Nitrogen's already filled. It doesn't have the room for hydrogen's electron. That would put 3 electrons in that orbital. We can only have 2. And so it just kind of shows you that the maximum number of electrons per orbital is still 2, just like it was back for electron configurations in chapter 6. So nitrogen's happy with 2 electrons here, spin paired, and then it has 1 electron in the p orbitals to make 1 pi bond, and then the other p orbital, 1 electron to make the second pi bond. So I don't know if, like, obviously this isn't a sketching class. Like, we're not going to take a test where we say, okay, sketch the MOs of N2, right? It's a multiple choice test. It's more about recognizing the picture. So the picture of N2 would have two bonds that look like this, just one of them on this axis, the other one sticking straight out of the page. And so, you don't have to sketch these structures so much as just recognize and understand and comprehend them, hopefully. And so for a quick summary, this is kind of what I was talking about. Well, like a quick summary, I think, would be that you're looking at the molecule first in terms of its geometry. I don't like that they chose HgCl2 here. I don't know why they put that as a choice. Like, I want us to have a molecule that we know the geometry of from Lewis structure rules. So by Lewis structures, if we know a molecule is linear, so all we have to know is from the Lewis structure, is the molecule linear? If so, like BeF2, like CO2 is probably a better example. It's going to be sp hybridized. So we're going to hybridize two orbitals. So we get two hybrid orbitals to get the pairing with the two things like CO2, BeF2, et cetera. So molecules that are linear go sp hybridized. Molecules that we know from their structures are trigonal planar. Let's write trigonal planar here. So if we can sketch a Lewis structure and understand the molecular geometry name would be trigonal planar, then that structure is going to go into the sp2 hybridization set. So anytime we have a central atom that has three bonding pairs and no pairs of electrons, and it's going to go sp2. And we can even have this as the geometry set for things like ozone. If you look at ozone, if you remember, we have this base Lewis structure here. That I want us to see that even if you have a lone pair of electrons here, that this could still be an atom we look at and say that that's sp2 hybridized, because I have 1, 2, 3 total domains. So anytime we have 3 total domains, we're in trigonal planar electron domain geometry, then we're in sp2 hybridization to describe the bonding of the central atom. And then we're in sp3 hybridization anytime the molecule is tetrahedral. The key is tetrahedral electron domain geometry. So CH4, ammonia, water, those are all molecules that are tetrahedral. They are all molecules you can describe with sp3 hybridization. So for water, if we're picturing the structure of water, let me start with oxygen though first. And let me start with the molecular geometry where I'm going to put almost like a tetrahedron first, put an electron pair in 2 of the spots, and then put hydrogen atoms in the other spots. And so we know we get this bent bond for water, and then the hybridization set for oxygen that we can choose is sp3 because we know the molecule is tetrahedral. Because we know the molecule is tetrahedral, it goes sp3, and then that allows us to understand the bonds with hydrogen are 1s sp3 overlap, and then the lone pair electrons on oxygen are just occupying the sp3 orbitals. So we have 2 lone pairs in sp3 orbitals. So lone pairs can occupy the hybrid orbitals. And then they're not available to overlap with other things because those orbitals are filled. They don't need to overlap with other electrons. So we don't make hydrogen bonds with those orbitals with an H atom because that would give us 3 electrons. We only need 2 for a bond or 2 for a pair. And so we end up with the lone pair with the H lone electron, the O lone electron making those bonds with water. So sp3 hybridization for anything tetrahedral. So a relatively, I think, straightforward question that kind of summarizes a very basic question like that you can put together with just like the minimal understanding of double bonds. Anytime I see a double bond, that this is a sigma plus a pi. When I see this bond here, same as well. It's a sigma plus a pi. I see this triple bond, that's a sigma plus 2 pi bonds. And so then in terms of sigma bonds, I have these single bonds are all just 1 sigma. So these are all just sigmas. And so in terms of my sigma bonds, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds. So I just counted all the singles plus each of the double bonds and then each of the triple bonds. So basically just every bond pair total up to 9. And then in terms of the double bonds, I have 1 here, 2, 3, 4. So again, I'm just counting the triple has 2 pi bonds. Each of the double bonds has 1 pi bond each. So that's a total of 4. So this is just coming back to single is 1, double is sigma plus pi, and then triple is a sigma plus 2 pi. So that's all we're using here on a problem like this. Now, again, like the tricky question would be sketch it. Like, I mean, that would be tricky even for me with like a ruler and a much better artistic ability. It'd be hard for me to sketch it. But if you can sort of get the idea that the hybrid orbitals are where we get bonding in the middle. So the hybrid orbital overlaps are where the sigma come from. The unhybridized p orbital overlap are where the pi orbitals come from. So unhybridized p orbitals overlap to make pi bonds, and then the hybrid orbitals or the native orbitals and the atoms overlapping with those orbitals give us our sigma bonds. So if I had just said, describe, this bond here, the hydrogen to oxygen bond, I would look at oxygen and say that's sp3, and that the hydrogen's orbital that it would overlap, it doesn't need hybridization, so we just say the 1s of hydrogen. So the bond, the hydrogen-oxygen bond is 1s sp3 overlap. Or if I said, describe to me the hybridization set, let me make this a little bigger here, describe the hybridization sets of all these atoms. These are sp2s because they're trigonal planar. This is an sp2 here as well because it's trigonal planar. And then these atoms here are sp because they're linear. So we have two linear groups in terms of carbon and nitrogen. So we can identify sp, linear, anything linear is sp, anything trigonal planar is sp2, anything tetrahedral is sp3. So if I count 4 total domains for oxygen, that's why it's sp3. So I think there's just one last thing to look at here, which is some of the pictures we get for, oh, sorry, one other question before we get to one last kind of topic we can look at. So classify the hybrid orbitals and approximate bond angles of essential atoms in a few molecules here. So the first one being acetic acid. And so this is acetic acid. So for picturing a Lewis structure, and I like to draw things flat because it's easier. Remember, we sketch a lot of Lewis structures flat and we'll interpret shape accordingly. We have carbon. What do I do here? Well, I'm going to have carbon bonded to oxygen as the central atom. And then we're going to, if I want to get 4 bonds onto carbon here, I need a double bond. We would probably not have you sketch the Lewis structure from scratch, to be honest with you. Like, I used to kind of be a little bit, like, if I were teaching this class, I would probably show you a few more examples of sketching a Lewis structure from like a base, like, formula. But that's pretty tricky. So I think whenever we want you to look at something like acetic acid on a test, we would just show you the Lewis structure instead of like making you sketch the Lewis structure. And so in total, we'd have a structure that looks like this. So in terms of our bond angles, we'd have the idea that this is sp3. Being sp3 makes these bonds have what angle? It's either 90 or it's 109.5. What do you guys think is the best angle for the hydrogen to hydrogen bond angle? So what do you think here? See, it looks 90 in the page, but it's not really 90 in reality. The reality is it's 109.5 degrees. So you got to remember, when you're sketching two-dimensional shapes, you got to interpret 3D shape that the molecule would really have. Like, for example, here, this bond's not 180. That would not make any sense. This bond angle here is closer to 120 degrees because that's trigonal planar. This bond angle here is not 180. That's more like 109.5 because this is tetrahedral. That's sp3. This sp2, trigonal planar group here. sp3, tetrahedral. So tetrahedral sp3 go together, sp2, trigonal planar go together, linear sp go together. We did this shape previously, so I'm not going to go back through that one again. Or actually, just a quick couple bond angles, 180 here, 120, and then 109.5 in terms of those bond angles. We're just, again, thinking it's tetrahedral, it's 109.5, trigonal planar, it's 120. We're like, you get these pictures. This is probably where I'll just pick up from next time. So next time I'll describe, to wrap up chapter 9.6 and then get into some review after, is you can make sense of some pictures of resonance with these orbital pictures. So let's make sense of that next time and then move forward into some review. And that'll do it for today. Have a great day, everybody.